Welcome back, folks. We're still working with transients. We've looked at a capacitor example and inductor example. They were both discharging. I wanted to get you one that was charging just because the numbers work out a little differently. And, you know, more is always better, right? Maybe. Anyhow, so we have another problem. It looks like this. And we're doing the similar kind of stuff. Oh, I couldn't get the font to work right. And I meant to do that before I started recording. VC. So we're just going right for the voltage across the capacitor. So this one should be a little shorter. That's what we're after. We're not going to use it to go find some other value for this problem. Okay. So the switch has been open for a long time. So here's this switch here, and we're going to grab the circuit. There we go. And say before t equals 0. The switch is open before t equals 0. All right, the switch is open, so that's just going to be open. There's no connection there, and we're once again going to assume that the switch has been open for a very long time. So the circuit is in a DC state, and now this is open here. So what we want is the voltage across that, and that's going to be our voltage at t equals 0. Okay. There are no meshes. There's no current flowing anywhere in this circuit, and that gives me some faith that that's going to be 0 volts. Okay, since the voltage here is really in parallel with the voltage across this resistor, there's no current flowing through that resistor, so it's 0 volts. Okay, after t equals 0, here we go, the switch is closed. And we're going to leave it closed for a very long time, long enough that the capacitor once again looks like an open. Okay, and we're interested in that voltage, and that's going to be the voltage at t equals infinity. I can do that cleaner. The voltage at t equals infinity. That's slightly better. Okay. Now, we've got to find that voltage, and it's effectively the voltage across R2 here. And we could do mesh if you want, but if you're really paying attention, that's really a voltage divider, right? So we can say VC at t equals infinity is equal to 15 volts times 6K over 6K plus 3K. Okay, so that looks like it's 2/3 of 15 volts, which is really 10 volts. Okay, we have our initial condition and we have our final condition. So we've got to go use those to find K1 and K2. So VC at 0 is equal to K1 plus K2, and that's equal to 0. And VC at infinity is equal to K1, and that's equal to 10 volts in this case. Now, it's real easy to screw this up if you move too fast. We're plugging in 10 volts for K1. What does K2 have to be to make this 0? Okay, and this is when I like to lean on the matrix form. It's always going to be 1, 1, 1, 0. Right? Invert it. Initial condition, final condition, and that's going to give us K1 and K2. Okay, K1 we know is 10 volts, and if you go ahead and solve that, I encourage you to do it. You're going to find that K2 is negative 10 volts. Okay, so that way when I plug in 10 here, I get negative 10 there, and I'm back to 0. This is a charging capacitor. It's not charging to 15 volts, it's charging to whatever voltage is seen across that resistor. Okay, we need, oh good, I still have the schematic. We need tau, right? So after t equals 0, the switch is closed, and we want to Thevenize around the capacitor and find R Thevenin. So from here, we want to find R Thevenin. We replace all independent supplies with the ideal resistance, which is a short, and then we figure out what that resistance is. So R Thevenin in this case, in my head I'm doing method 1. 6 is in parallel with 3K. They're both connected to this node up here, and they're both connected to this node down here. So R Thevenin is 3K in parallel with 6K, which is known as 2 kiloohms. That's a common enough one that I'm not going to plug it in my calculator, but sometimes you got to use a calculator, right? It's 3K in parallel with 6K. Tau is then R Thevenin times C, whatever that is. So it's going to be 2K times 200 nanofarads. I got that from the first schematic up here. Okay. 200 nanofarads. So if I go ahead and now I'm going to use the calculator because I don't trust myself with exponents. 2K times 200 nanofarads. Nano, -9, E -9, right? So that's going to be 400 microseconds. Good stuff, huh? Writing it all out, we get VC as a function of time. K1 was +10. K2 is -10. E to the negative t over 400 microseconds. Now the 10 and the 10 both get the unit, and luckily they both end up being volts. If one was millivolts or kilovolts, we'd have to do some moving around because that unit belongs to both of these constants. And that's it. Okay, so that's a charging capacitor. Come on, make my special little things there. That's a charging capacitor. It's still a voltage supply. If I wanted to go find other values in the circuit, I could come back and grab the original circuit and replace it with a voltage supply and then do some superposition if I had to. But we've done a couple of examples of that. We're going to do some more, so I don't think it's entirely necessary on this problem. Okay, throwing examples at you, hoping they're helping. I think they are. You tell me. Certainly in the live sessions, in the comments, or if we have the text feed for class, I'm always happy to hear if this is working for you. Okay, more coming at you. Stay tuned and good luck.